I'd like to introduce our first speaker, Holcomb. So I'll wait for him to get up here. Thanks. Okay. Cole did his PhD, or is doing his PhD at Princeton University in physics and astrophysics. His advisor is James Stone. He's a fourth-year fellow. He did his practicum at Los Alamos National Lab in 2015, and today he will be telling us about gyroresonant streaming instability of interstellar cosmic rays.
Thank you, Jennifer. Can everyone hear me? Okay. So I guess I'm kicking off the astrophysics block of talks here, and I thought a good way to do that would be to show a nice pretty picture of a galaxy, as we do in astronomy so often. So this is the galaxy M82, also called the Cigar Galaxy. And what's particularly interesting about this galaxy is that, as you can see, kind of going from the bottom right to the top left in red, there's sort of this large-scale outflow being driven out of the galactic disk. We call this a galactic scale wind, and it's a big open question as to how these outflows are actually driven in this environment. We will see soon how this has anything to do with cosmic rays. So just to give a brief outline, first I'd like to tell you exactly what a cosmic ray is, and then getting back to the title slide, why they're important. I'll discuss briefly some of the relevant physics that goes into the cosmic ray interaction with the interstellar medium, and then I'll give you a small flavor of what I've done on my thesis work. So, of course, we need to start with what is a cosmic ray. Well, very briefly, a cosmic ray is just a relativistically traveling, so moving near the speed of light, charged particle propagating in outer space. So very simple definition. If we want to get into a little more detail, they're mostly bare protons, so protons that have been stripped of their electron, propagating through the interstellar, intergalactic, intracluster media with giga-electron volt energies. So energies comparable to their own rest mass. You can see in this figure, which is sort of the quintessential cosmic ray observational figure, on the x-axis we have the energy of observed cosmic rays, and on the y-axis we have the flux that we observe at these energies. And you can see that there's a very nice power law extending over 10 orders of magnitude in energy. So very energetic particles. On the bottom we have comparable energy scales for terrestrial particle colliders. So the largest energy cosmic rays are actually exceeding by several orders of magnitude what we can produce in the laboratory today. So these power laws we think come from acceleration by interstellar shocks. The cosmic rays we observe, they're isotropic, they're coming from every direction equally. And then finally, they are collisionless gas. So they don't interact strongly via Coulomb collisions with particles in space. And on top of that, they're very sparse. There's not very many of them. If you take a typical density in the interstellar medium, it's like 1 particle per cubic centimeter. The cosmic rays are much less dense than that, by up to 9 orders of magnitude. But despite these small densities, there's actually a large amount of energy stored in the kinetic motions of these particles. If you take the components of the interstellar medium, break it into sensible categories, you can look at how much energy is stored in each component. You can say the cosmic microwave background, starlight, turbulent and kinetic motions of interstellar gas, and then finally you look at the cosmic rays, you can see that all these components have roughly the same amount of energy stored in them, about an electron volt per cubic centimeter. So despite their small number densities, you might expect cosmic rays to actually be able to influence a large effect on their surroundings. So how do we study cosmic rays? Well, in my mind, we can break this into basically 3 questions. The first of which is, where do they come from? As I mentioned, we believe they come from shock acceleration. So you can do simulations of this. And what I'm showing here is a simulation done by collaborators in my group of essentially a shock. What they do is they send in a flow of plasma from the right boundary, it rebounds off the left boundary, and then essentially starts colliding with itself, which forms this shock structure that you can see here. On the top panel, we're showing density. You can see that the density is much higher on this left side than on the right. On the bottom, we're showing the magnetic field. So on top of the density increase, there's also some magnetic amplification going on. So here is another view of a very similar simulation. Again, on top we have density, on bottom we have magnetic field, but in the density plot we're also showing some tracer particles. You can see them sort of streaming in from the right, and they have these little tails, and the tails are representing how much energy they contain. And you can see as they scatter off the shock boundary, they increase their energy. And in the top figure, we're showing a energy spectrum of particles that over time, with blue being earlier, red being later, initially you have just a nice Maxwellian distribution, and over time a power law tail develops, and this is describing the shock acceleration of cosmic rays. So second, you can ask, where are they going? Well, for us, they're going here, where we observe them. So the observational question, I think, is sort of the next step. Here is a sort of artist's imagination of the Pierre Auger Observatory in Argentina, I believe, looking at the cosmic ray showers as they scatter on Earth's atmosphere. And these kinds of observations can lead to the sort of figure I showed previously of this nice power law energy spectrum of cosmic rays. And then finally, you need to ask, well, we know where they started, we know where they end, but how did they move in between? And that's when you get into cosmic ray transport, which is more of what I do. But unfortunately, the scales of the problem range from the interaction scale of cosmic ray, which is defined by the gyro radius of these cosmic rays, typically about an astronomical unit, and then all the way up to the size of galaxies, which is thousands of parsecs. So huge, huge separation of scales there. So if you want to study this, you need to sort of break it up into two parts. And we break it up into sort of the microphysics, where you look at the kinetic theory of particles, you do kinetic simulations, and then you can also break it up into the large scale with the fluid theories. So if you do want to do a fluid theory of cosmic rays, essentially what you do is you take the regular fluid equations, conservation of mass, conservation of momentum, energy, magnetic flux, and so on, equation of state. And what you do is you add in terms that model the effect of cosmic rays on the fluid, the energy and momentum distribution that cosmic rays can give. And you can run simulations like this, fluid MHD simulations, which this group from Germany did. And they produced these nice figures where what you're looking at is a model galaxy disk on, or edge on, and the X is just right. So the X is just across the disk, and the Y-axis is out of the disk. And what you can see is between the bottom and the top, the bottom has the cosmic ray effects turned off. The top has the cosmic ray effects turned on. And what happens is that when you don't have the cosmic rays, you're unable to drive these galactic scale winds, whereas if you turn it on, suddenly these large-scale outflows start forming. So the parameters matter, but we don't really have a sense for what the parameters should be. So that's why we need to turn to these microphysical simulations to understand how to pick these input parameters. So the microphysics is sort of determined by what we call the self-confinement paradigm. Like I told you, cosmic rays originate from shocks. These are point sources. But we also observe them to be nearly isotropic. So that means that somehow these point sources need to be scattered strongly as they propagate through the interstellar medium so that by the time they reach us, they're isotropic. And for that to happen, you need fluctuations to scatter on. And the way you get these fluctuations is through this, what we call the cosmic ray streaming instability. The cosmic rays generate the fluctuations that they then subsequently scatter on, and that's why we call it self-confinement. So in order to scatter on waves, you need to meet special conditions, and that's called the wave-particle resonance. Here I'm showing what's called the Landauer-Cherenkov resonance condition, which is a condition between the properties of the wave and the velocity of particles. It says that in order to resonate with a wave, the phase velocity of the wave has to match the velocity of the particle, or that the Doppler-shifted frequency of the wave in the particle frame is 0. In that frame, your particle will see a constant electric field and will be able to interact very strongly with that field. And just a nice, easy analogy, this is very similar to surfing. So here I have a typical surfer, and presumably what this dog did was he was sitting out on the ocean looking for waves. He spotted a wave and he immediately started paddling. And the reason he was paddling was to match his speed with the wave so that he could then ride the wave and look super cool. So that's how wave-particle resonance works, roughly speaking. So for cosmic rays, it's a little more complicated. And actually in surfing, it's more complicated than that too. So in plasma physics, the sort of quintessential task is to derive a dispersion relation for your waves. And if you do that in the cosmic ray system, you can show that waves will be unstable under certain conditions with a growth rate given by this equation. And I just wanted to point out some important features of this growth rate. First of all, you can resonate with waves of different polarizations depending on the circumstances. There's a delta function in there that encodes this resonance condition that I just talked about. Here we're talking about gyroresonance, whereas before we were talking about a longitudinal resonance. So it's a little bit different, but not too much. And then finally, there's this term in brackets which depends on gradients in the cosmic ray distribution function, and that is essentially encoding the fact that if you have anisotropy in your cosmic ray distribution, you will be unstable. And this anisotropy is called streaming, which is giving this instability its name. But ultimately, the idea is just that if you have some bulk motion of the cosmic rays will push on the waves, and the waves will gain energy and momentum from that mechanism. So if you have cosmic ray anisotropy, you will get instability. But what do we want to know? We want to, first of all, validate the linear theory, the equation that I just showed, among other things. But we also want to go beyond that. Linear theory can only get so far. So linear theory says nothing about the saturation of the instability. Presumably it can't go for forever because the cosmic rays don't have infinite energy to give. So at some point the instability has to stop. We want to know when and how that happens. And then we also want to know how the cosmic ray distribution function looks at late times. So to study these questions, we use particle and cell simulations. I can talk about that with you offline if you want to know more about it. But essentially what we do is we put in a background plasma with Maxwellian distribution, just a regular background plasma. And on top of that, we inject a population of cosmic rays with whatever distribution we want. And on top of that, we have electromagnetic fields with a background, and in particular, a background magnetic field that goes along the x direction. An important point is that the cosmic rays have to be traveling with a bulk motion that's faster than the Alfvén speed in order for this instability to work. So here I'm showing just an example initial condition from a simulation that I've run. On the x-axis, we just have the x-coordinate. On the y-axis, we have the momentum along the x direction. And then the color is representing the density of particles in that cell of phase space. So this thin little yellow line is representing the background. It's very cold, so it's very thin on the plot. And then there's a much broader sort of cloud-looking population, which represents the cosmic rays here. So one particular cosmic ray distribution that we can use is just a beam. It's given by this f down here. It's just two delta functions. You pick a momentum, you pick a pitch angle cosine, and that determines the momenta for all the cosmic rays. The figure is showing the progression of the parallel momenta, the transverse momenta, and then the transverse magnetic field from top to bottom over time from left to right. At early times, you can see that the cosmic ray distribution is very beamed. It's just starting to interact with the magnetic field, so you get these little bubbles forming in the parallel momenta. In the middle frames, you can see that eventually very large amplitude waves grow, and this is represented in both the magnetic field and the transverse momenta of the cosmic rays. You can see a very resonant structure as the cosmic rays are forced to oscillate with the magnetic field. And then ultimately, all this structure is sort of broken up by nonlinear effects. So a more realistic distribution would be the power law distribution, which is what I spent a lot of time on. Here I'm going to show a little animation of a simulation. In the top left corner, we have, again, this momentum, X momentum density. On the bottom left, we have the transverse magnetic field. On the top right, we have the magnetic field spectrum in Fourier space. And on the bottom right, we have the magnetic energy over time. So there we go. So again, it's a very similar thing. The cosmic rays are initialized. Over time, they start to interact with the magnetic field. The magnetic field grows. Waves start being pumped up. But ultimately, they reach a large amplitude, and nonlinear effects start to come into play, which disrupts the cosmic ray distribution heavily and ultimately quenches the instability. So if we look more closely at the magnetic energy growth over time, you can see there's a few different phases. Initially, there's an equilibration phase as the background plasma goes into equilibrium with the electromagnetic fields. But out of this initial phase is a linear exponential growth phase, where which is given very well by the equation I showed previously. Ultimately, there's a saturation phase. The growth of the instability abruptly slows down, and then there's sort of this drawn-out nonlinear phase at the end. So you can examine this in terms of both the magnetic fields and the particle distributions. Again, on the top, I'm showing the magnetic energy over time for several different simulations that I ran, and on the bottom, I'm showing the drift velocity of cosmic rays over time. In this case, they're all starting at 5 times the Alfvén speed, and as you can see, only some of them are actually being fully isotropized or being slowed down to the Alfvén speed. And so this is kind of an important and unexpected result. It was expected that always cosmic rays would be fully isotropized, fully brought down to the Alfvén speed. But what you can see is that in the case where the instability doesn't grow the waves to large amplitude, the cosmic rays are unable to fully isotropize. For example, in this red line, the wave amplitude doesn't reach. The wave amplitude saturates at about an order of magnitude less than the other simulations, and this is reflected in the bottom panel where the Alfvén speed is saturated with an anisotropic drift. And then we can look at this again in the cosmic ray distribution function, just to understand how the saturation is working. In the top panel, I'm showing the initial condition of the simulation, and in the bottom panel, I'm showing the cosmic ray distribution function at the time of saturation. So if we go back to that equation I showed for the growth rate, there's this term with the distribution function gradients. This term is essentially controlling when the instability ends. If you look at the bottom panel here, you see that at the time of the saturation of instability, there's this very large area where the distribution function is flat. The contours are flat in both the momentum and pitch angle distributions. But notice that the distribution function is not flattened across the entire range of the pitch angle cosine mu. There's actually a detail that I didn't mention, which is called the 90-degree problem, which says that the Alfvén waves are unable to scatter forward-moving particles into the backward direction, and therefore there's sort of this invisible wall at mu equals 0, which particles aren't able to scatter through. So this is sort of the thing that leads to the early saturation of the instability that I showed in the previous slide. And then finally, you can, then using that information, you can sort of estimate when the instability will saturate using just simple conservation of momentum arguments. You say, well, initially there's some momentum in the cosmic rays. As the instability progresses, the distribution function will be disturbed. You'll be isotropized, and you will give that momentum into the magnetic waves. And just using simple differences, you can argue that there will be some amplitude of the waves at the end of the instability. And so what I'm showing here is just again, this RMS amplitudes of the magnetic waves, and the horizontal lines are showing my predictions, which are more or less spot on. So I'm out of time, and then briefly just want to thank, of course, the NNSA for this wonderful program and Krell Institute for organizing it. It's been a really great experience, and I've been very happy to have been a part of it. And thank you all for your attention.